Greetings of the day to all of you. Welcome to the 13th lecture on modern power electronics. As part of module 2, we have finished the design aspects in power electronics, where we have discussed the design of various components in power electronic circuits. We will now move on to the second part of module 2, which is resonant converters, or you may also call them as soft switching DC to DC converters. Basically, soft switching or the phenomenon of resonant switching can be used in any type of converter, whether DC to AC or AC to DC or even AC to AC. But resonant converters are most common in DC to DC topologies. Therefore, they are mostly studied for DC to DC converters. Now, what exactly is a resonant converter, or what exactly is a soft switching technique? Before we discuss resonance and soft switching, we will discuss our usual hard switching or switch mode power converters. So basically, when you talk about a power converter, it is generally a switch mode converter, which means it is either on or it is off, and depending upon whether it is on or off and how we turn it on and off, we may achieve control in the form of AC to DC, or from DC to AC, or from DC to DC, or from AC to AC. So all types of power conversion is possible by rapid switching of power electronic devices, on and off switching of power electronic devices. And we also call it switch mode power conversion because each device is operated like a switch on and off, mostly in its saturation region. Now, whenever we talk about a switch mode power converter, we also know that our attempt is always to increase the switching frequency, because we have studied also in the previous semester, as well as in the initial lectures, that increasing the switching frequency miniaturizes our power converter. So it reduces the size of L, it reduces the size of C, and basically it helps you in designing a very small power converter if you increase the switching frequency. However, when you increase the switching frequency, you also increase the switching power loss, which we have already derived to be equal to VI upon 6, the turn on and turn off transition times of the device, into the switching frequency. So if the switching frequency is high, and if the voltages and currents during commutation are high, then the power loss is bound to be very high. So whenever you try to increase the switching frequency in order to miniaturize your circuit, you end up in producing too much of switching power loss. Not just producing too much switching power loss, but you are also very often introducing unnecessary, undesired electromagnetic interference in the system, because as you increase the switching frequency, your switching time intervals decrease, and as a result of that, dV by dt and di by dt phenomenon, because these intervals become smaller, therefore dV by dt and di by dt phenomenon become more pronounced, as a result of which you see common mode voltages and common mode currents, undesired common mode variables flowing in your circuit. So these are the you can say side effects of increasing the switching frequency. But when you talk about your conventional power converter, this is how it has switching losses. So this is when its turn on or turn off behavior is governed by these switching losses. It also means that if the commutating voltage or the commutating currents are high, then in that case it is even more difficult to increase the switching frequency. So not just that the power loss depends upon the switching frequency, but it also depends upon the commutating voltages and commutating currents. The concept of soft switching DC to DC converters, or you can say resonant converters, is to cause something like a zero current switching, often called as ZCS, or a zero voltage switching, also called as ZVS. So basically they ensure that when a device undergoes commutation, whether it is turning on or whether it is turning off, at least during the switching, you know that during the switching there was also voltage as well as current across the device, and hence there used to be some power loss. But by ensuring soft switching techniques, we basically make sure that while the device is switching from off to on state or from on to off state, at that time either the current through it is zero, so that the voltage may change but the current remains zero, or the voltage across the device remains zero. In either case, your switching power loss will be minimized. So when you are doing soft switching, even though your switching frequency may be drastically increasing, but because one of these two terms is zero, therefore you are contributing to almost zero switching power loss. Now, how we achieve zero current switching and zero voltage switching, that is what resonant converters is all about. So we basically make use of the concept of LC resonance to achieve zero current or zero voltage switching. So again, we make use of some passives, very small sized passives, along with the switch, that help us in achieving minimum loss, and therefore we are reducing switching power losses. Therefore we allow our converter to operate at very high switching frequencies, and we also tend to reduce EMI problems by means of resonant converters. So this was about what exactly resonant converters do. So this basically they are meant to cause almost negligible switching power losses by either causing the voltage or the current to be zero during the switching process. Right? Now, before we discuss resonant converters any further, let's recapitulate our previous studies on switch mode converters. So whenever I have to turn a switch on, a fully controlled switch on, I issue a gate pulse between its gate emitter terminals, something like this. So this is between V, G and E. Now what we know so far from our previous lectures is that as soon as the gating pulse is issued, the very same time the current through the device starts increasing. And at the same time, though there was voltage, because previously the device was off, so it was blocking some voltage. Say it was blocking some voltage, let's call it say V, and then it was not carrying any current. Initially the current was zero. The moment you turn the switch on, the voltage started falling and the current started rising, of course with a small kick due to the presence of junction capacitance. So there is a small C dV by dt kick in current during turn on, and then your voltage has fallen to almost zero value, right? So this was the turn on transient, and now let's see the turn off transient. Now when the pulse to the device goes off, what happens is that the current across the device starts falling, and at the same time the voltage across the device starts rising, of course with a small kick in voltage present that is caused due to the stray inductances that are present in the circuit. We have discussed this previously in our initial lectures when we started with gate driver design. We basically started with understanding the behavior of a switch, and even in Snubber circuits we have understood this concept. So capacitances are bad during turn on and inductances are bad during turn off, right? This is what we know so far. And we also know that this switching power loss that happens as the devices undergo switching, this as well as this, is totally equal to Vi upon 6 T on plus T off into Fs, where Fs is the switching frequency. Quite obviously, this also tells you that higher the switching frequency, higher will be the loss, and higher the values of voltages and currents that are commutating, that are transferring during turn on and turn off process, higher will be the switching power loss, right? But unfortunately, in most power electronic circuits, you will observe that devices actually do not commutate like this. A device will, when it is switching, it will show slightly different characteristics than this. Now let's see what happens in most converters, how devices actually undergo the switching process. To understand that, let's take a practical example of say a half bridge, or you can say an inverter leg. I have previously also discussed with you that this is a fundamental building block of most power electronic converters, whether it is inverters or DC to DC converters. Half bridge is a very fundamental building block. Now assume that you have a switch and then you have a complementary switch on the half bridge. This is S1 and this is S4. They also have anti-parallel diodes. So these are basically diode clamped devices, most commonly used in power electronic circuits, whether it is DC to DC or DC to AC converters. So say this is one leg of an inverter. This is the input DC bus. Let's call this bus as VD. And this is the output current. Let's call it IA. We also know that S1 and S4 are complementary. Now in a small switching interval, whether you are switching from S1 to S4 or you're switching from S4 to S1, in every small switching interval, we assume that IA is constant, because basically IA is a low frequency signal, say a 50 Hertz signal, but the switching frequencies, they are corresponding to say 10,000 Hertz or 20 kilohertz or 30 kilohertz or even more. So when you compare the waveform of IA to the high switching frequency of the devices, then IA over a small interval may be assumed to be constant. So let's assume that IA is constant, and in some switching instant it is positive, so it's flowing in this direction, right? It also means that if I want to suppose say switch on S1, so I have given a pulse to S1 and I want to switch it on. Let's see the behavior of S1 while turning on. So this is the pulse that I have given between the gate emitter terminals of S1. As soon as I gave a pulse to S1, S1 will start conducting. But before that, it was D4 that was conducting this positive current, because I'm assuming a constant current for now. So obviously this current was being carried by D4 before I gave a pulse to S1. Now what basically happens is that when I give a pulse to S1, the current through S1 starts rising. Of course, it has a small C dV by dt kick, right? So this is the current, say IS1, and in steady state, it takes up the whole load current IA. Okay, this is about turn on. Let's talk about the voltage across the device S1. Before S1 was on, the voltage across S1, we can call it VS1, was simply the whole, because D4 was conducting, so it was a whole DC voltage appearing over here. So before S1 was conducting, the voltage across it was VD. So VS1 was equal to VD, right? Now at this instant, you have issued a gating pulse to S1 and S1 has begun conduction, or you can say that the current through S1 has started to increase. You're also assuming a stiff current at the output. Okay, so the output is behaving like a current source. There is a stiff current at the output, which means that when S1 starts taking up this IA, D1 will start giving away this IA. Or in other words, as IS1 increases, D4 will start, the current through D4 will start falling, which also means that as long as IS1 does not reach IA, till then the current through D4 will not reach 0, because I have to ensure that this current, the current of S1 and the current of D4 together make up, say, SIS1 plus ID4. They should together make up IA, right? Now, when you switch S1 on, this current starts falling and this current starts rising. This current starts rising and this current starts falling till the time IS1 becomes equal to IA. D4 will keep falling, and as soon as IS1 reaches IA, only then ID4 will become 0, because we have maintained a condition that IA is constant, the load current is constant. Now, it also means that from here all the way up till here, D4 is continuously in conduction. And when D4 is in conduction, it also means that voltage across device S1 is still equal to VD. Which means that previously we assumed that as soon as the current starts rising, the voltage starts falling. But in diode clamped power electronic circuits where devices are diode clamped, you also see that because of the conduction of the previous device, the voltage across the incoming device S1 does not fall to 0 as long as D4 conducts. And as long as D4 conducts, this plus is here, this minus is here, so the entire DC link appears across the switch. So voltage across the device remains constant as long as there is current through diode D4, and only when the current through diode D4 becomes 0, or you can say that the switch current becomes equal to the load current, only then will your load device voltage start falling. So after that, your device voltage starts falling, and now you can safely assume that your device has turned on. So your device remains on, carrying some current with 0 voltage drop across it for some interval. All right. Now what happens here is that at this interval you have withdrawn the gating pulse to the device. Now when you withdraw the gating pulse to the device, the voltage across the device starts rising. So the voltage starts rising, of course, with some LDI by dt kick. Which means that at this interval, the voltage across S1 is rising, or you can say the voltage across S4 is falling. You have to ensure that the input DC voltage is somehow accommodated within these two switches. So VS1 plus VS2. As soon as you withdraw the gating pulse to S1, its voltage will start rising, and of course this device has to go into conduction, so the voltage across this device will start falling, right? Now, as long as VS1 has not reached VDC, VS2, or you can say VD4, will not reach 0, which means that as this voltage VS1 is increasing up to VDC, this voltage over here is falling, and it will not reach 0 as long as this voltage reaches VDC. When this voltage has not reached 0, which means there is some finite voltage across the device, it also means that the diode D4 is reverse biased, so the diode D4 cannot start taking up current, which also means that S1 will continue to take that current. Therefore, S1 will continue to take current till the voltage is completely shared by S1 and D4 voltage across D4 is 0, and therefore at this interval D4 will start taking current, or its current will start rising, and the current of S1 will start falling. So only after this interval you will observe that the current will start falling, right? So this was about actual switching in most power electronic converters that do not use any snubbers. What basically happens is that when we were studying about switches, we were assuming that if current is rising here, voltage will also start falling here, right? And if voltage was rising here, current will also start falling here. This is what we were assuming previously. But because voltage stays for some time while the current increases, and the current stays for some time while the voltage increases during turn off, because of this you see that in diode clamped power electronic circuits there are actually more losses, right? Because earlier in this interval there used to be switching, right? In this interval, because voltage would be rising and current would be rising and voltage would be falling, but here voltage is constant and it's high, so obviously there is more area under the curve. There's more area under this curve as compared to what we had calculated. So there are more losses in practical power electronic circuits. Not only are there more losses, I will also try to put this information in the form of another graph. What basically happens in diode clamped devices is that the turn on and turn off process put on a lot of stress on the device. Suppose this is the voltage across the device Vs1 and this is the current through the device, say Is1. And initially let me assume that the device is off. So when the device is off, it is blocking some voltage which is equal to the DC link voltage Vd, and it is not carrying any current, so it is on this line, right? So it's over here on this point, actually not on the line, on this point. So now that it is on this point, it is off and I want to turn it on. And when I want to turn it on, just now I have drawn the graph. I know that when I turn, suppose at this instant I turn it on, the current will start rising till some finite value and the voltage will fall only when the current has risen, and this is because of the diode clamping. So let's see what happens in this interval. The turn on process. The voltage remains constant and the current starts increasing. So the voltage remains constant and the current starts increasing like this. By the time the current almost reaches its final value, of course with a small kick. So if this is the final value of the current IA, it will exceed IA by a small kick due to the LDI by dt, due to the CdV by dt kick. And then after that, the current will remain constant and the voltage will start falling. So the current will remain constant on this line and the voltage will go on falling. So you'll retrace like this, right? So this is the turn on curve of a diode clamped device, right? And if you do the turn off curve, when you turn off the device, so assuming the device has now turned on, so it will be operating at this point. It will be carrying some current and the voltage across the device will be almost zero. So it will be at this point. Now you have to turn the device off, right? So let's see how the device actually turns off. So it's on, so it's carrying some current and the voltage across the device starts rising. And it has a small LDI by dt kick, and the current, which is shown in green, does not fall until the voltage has completely risen. So this is I and this is V. This is V and this is I. This curve is for turn on and this curve is for turn off. Now at turn off, there is some current initially in the device and there is almost zero voltage, right? So this is zero voltage and some current. Now the current remains constant and the voltage starts rising. So the current remains constant and the voltage starts rising. So voltage is rising. I'm going like this. Current is remaining constant until I reach a point where the voltage exceeds its VDC value. So if this is the VDC value, the voltage exceeds that value and then settles back to VDC, and the current then starts falling. So the current then begins to fall at constant voltage. So the blue curve is the curve for turn off, right? And this kick is an L di by dt kick in the voltage. What does this tell you? This tells you that there is going to be a lot of area in the VI curve, lot of power loss. This also tells you that you have to take a big voltage and current rating of the device. So this is a safe operating area. Because you need to accommodate the C dV by dt kicks and L di by dt kicks, therefore you have to choose a voltage rating greater than the DC link voltage and a current rating greater than the load current, the rated load current. So the red curve over here is a safe operating area. You have to ensure that your curves lie within the the safe operating area. So you have to choose devices of higher ratings because your devices will undergo a lot of stress, voltage and current stress. Also, like I said, that in these devices you have more EMI problems. If I use a snubber, I will try to get a waveform where these peaks are also suppressed and also where the voltage will start falling, and over here at this point only the voltage will start falling over here only, the switch that we had discussed in the initial lectures, and here the current will start falling over here only because of the presence of a snubber, right? So because of that you will change your trajectory. If you use a snubber across these devices, say you have a device like this, you will use a snubber, a turn off snubber. We have discussed this in detail previously in the snubber design. This is a turn off snubber and this is a turn on snubber, which is not used very often. How these diodes and resistances come into play, we have already discussed that. And of course it is a diode clamp device, so if it will have its own anti-parallel diode. This is the switch and this is a snubber. If you use this kind of a circuit, then you will ensure that because of these snubbers, the device's voltages and device currents will show a transition much earlier, which means that when you turn on the device, the current will start rising and the voltage will start falling instantly rather than waiting and then falling. Similarly, when you turn the device off, the voltage across the device will start rising and the current will start falling almost immediately. Also, these C dV by dt's and L di by dt's, their magnitudes will be lesser, which also means that with a snubber in a diode clamp circuit, you are modifying the trajectory. This is voltage across the switch, this is current through the switch. Initially the switch is off, so it is blocking some voltage. You have to turn it on, so at the same time the voltage across the device will start falling and the current will start rising. So voltage starts falling and current starts rising, something like this. So this is your turn on curve, turn on. And when you turn it off, you have reached this point, that means you're carrying some current and there is no voltage across the device, and now you want to turn the device off again, then obviously the current through the device will start falling and voltage will start rising. So current will start falling and voltage will start rising. So this is turn off. Very obviously, if you compare it with the non-snubber device, जो कि कुछ ऐसा था, they were curves like these. You are operating with less area under the VI curves, so there is less switching power loss. You are also not subjecting your devices to too much stress. Earlier your safe operating area was this, now your safe operating area is this. So with snubbers, your devices are better protected, and you can even go deal with less rating of devices, right? So your devices are also subjected to less switching stress. But although you have reduced switching losses with snubber circuits, there is a lot of likelihood that you may have overall decreased the efficiency because there will be losses happening in these resistances, snubber resistances. So although the switching losses might be reduced, but snubber losses might be incorporated into the circuit, which will overall not really help your efficiency much. Therefore, in power converters where you are dealing with high power, which means high voltages and high currents, and where you want to still miniaturize a circuit and allow very high switching frequencies, there you tend to go for soft switching or resonant converters, which basically do zero voltage switching or zero current switching. Let's see what that is. So you have given a gating pulse to your device, VGE, and what happens is that initially the device was off, so it was carrying, there was some voltage across it and no current through it. Now, by zero voltage switching or zero current switching, what happens is that first the voltage will fall while the current remains zero, and then the current will rise while the voltage is zero. So this is your turn on process, which is a zero voltage switching process over here, which means that voltage becomes zero and then the switching happens. So power loss is zero, power loss is zero, right? And then let's assume a wider pulse. Right? And then the device is on, it's carrying current, it's dropping zero voltage, almost zero voltage, all the way till you suddenly turn it off. And when you turn it off, first the current falls, the voltage remains zero, and then the voltage starts rising, and then it acquires some peak value and current becomes zero. So again, this is device turning completely. This is the turn off interval, and once the current has fallen to zero, only then the voltage switching will happen. So this is current has fallen to zero, so this is ZCS switching. So at zero voltage you let the current increase, or at zero current you let the voltage increase, right? So this is zero voltage switching, zero current switching, which means that your losses are minimized, almost zero. So this is when your device is on, this is when it turns completely off, right? How we basically achieve ZVS and ZCS, that is also what we have to discuss. But if we see the VI curve, right, if I want to see the voltage current curve, this is voltage across the device, this is current through the device. Suppose the device is off, so it is blocking some voltage without carrying any current, right? First the voltage will start blocking, the voltage will start falling, so without any increase, or say marginal increase in current. So voltage will start falling, and once voltage has fallen to a near zero value, only then the current will increase. so only then the current will increase, right? So the turn on curve looks something like this, right? And the turn off curve, let's see how that looks. You are on, so you're carrying some current, and now you want to go turn it off, which means first the current will fall without any change in voltage. The current will fall without any change in voltage, and then the voltage will increase without any change in current. So just see, there is almost negligible area under the curve, so there is negligible switching power loss, and you are well within the safe operating region. Very less switching stress on the device. You don't even need a snubber. Basically, you replace the snubber components with a resonant passives LNC that resonate, and they help you in achieving zero current or zero voltage switching. Now, before we start discussing how it is actually achieved in a converter, I would also like to tell you something more about resonant converters. Resonant converters are broadly of many types. One are the full resonant converters, where you basically use the concept of resonance between L and C, where you use some additional L and C in a circuit that are always in a condition of resonance, which means they are always resonating. And these types of resonant converters are not very popular. But what is most popular and what is most commonly used is the quasi-resonant circuit, or the quasi-resonant converters, which basically use L and C components. You make them resonate at during some intervals, during some switching intervals. So you use L and C, and you also use a PWM scheme, a switching scheme, and you use them very intelligently, that during some interval of switching, L and C will resonate and not the rest of the time. So you make them resonate only during some intervals that help you in achieving zero voltage switching or zero current switching, and therefore you call them quasi-resonant converters. Most commonly you may just simply call them resonant converters. They will still be like have PWM plus LC resonating stage. So resonant converters or quasi-resonant converters may be used interchangeably from now on. We will I think in the next lecture we will actually begin with resonant converters topologies. We will first start with zero current switching topologies. So zero current switching topologies, they are different than zero voltage switching topologies, and sometimes you may use a combination of both, zero voltage switching as well as zero current switching. So that's all for today. I hope this lecture was clear to you. If you have any doubts or queries, you know that you have to ask on the WhatsApp group. And once we finish resonant converters, only then we will go back to data sheets and going back to solving problems on design. So that's all for today. Have a great day.